Welcome to our MathLINks webinar, Dig into Proportional Relationships Paint Mixtures. I'm Shelley Kriegler, one of the authors of MathLINks. Our presenter is Mark Goldstein, another MathLINks author. Take it away, Mark.
Thanks, Shelley. Let's get started. In this session, we're going to use an intuitive context with visuals to explore proportional reasoning problems. The visual will easily translate to introducing a tape diagram. Then we'll use the tape diagrams and proportion equations to solve problems. First, let's make a distinction between proportional reasoning and proportions. Proportional reasoning involves comparing quantities multiplicatively. For example, if you can buy 4 pencils for $1, then at that price, you could buy 8 pencils for $2. A proportion is a special kind of equation. It states that the values of two ratios are equal. Incidentally, the writers of Common Core chose not to use this word in the content standards. They consider it an unnecessary extra layer of vocabulary because it's just an equation. Here are some common tools or representations we use in middle school to explore proportional reasoning. Our paint mixture pictures are going to connect directly to tape diagrams, and then we'll connect tape diagrams to proportion equations. These paint mixture cards represent mixtures of blue and white paint. All of these little rectangles are intended to represent the same quantity of paint. Without much prompting, students can begin to try to arrange these from lightest to darkest. This should generate lots of discussion. In the spirit of the math practices, let's make viable arguments and critique the reasoning of others. Jody said mixture B and mixture C will be the same because they both have the same number of cups of blue. What's wrong with her thinking? They clearly do have the same amount of blue, but B has much more white than C, so B must be lighter. She's not thinking about the relationship between blue and white. Ed said mixture A and mixture D will be the same because mixture A has 1 more cup of white than blue, and mixture D has 1 more cup of white than blue. What's wrong with Ed's thinking? Ed is thinking about the relationship between blue and white, but he's using additive thinking instead of multiplicative thinking. Let's help Ed think through this one. Here's a double batch of A, and since this is a proportional increase, it must be the same shade of blue. One way to look at this mixture is to match up 2 blues for every 2.5 whites. Doing the same for D, we can now see that A has a little extra white, so it must be lighter. Another clever way to look at this comparison is to think in terms of a least common multiple to make the same amount of blue. What shall we make 12 parts blue for both mixtures? 1, 2, 3, 4 copies of A, and 1, 2, 3 copies of D. And now we can compare 16 parts white to 15 parts white. So again, we see that A must be lighter. Here's what a tape diagram might look like for mixture B. We offer 2 common techniques for drawing them. Equal-sized rectangles are used to represent the equal parts of blue and white, and the blue and white are clearly marked. Let's examine how Alex and Andrea solved this problem. How many gallons of blue paint and white paint are needed to make 12 gallons of paint using mixture B? Alex draws the 2 blue to 4 white ratio, which is 6 total parts, then proportionally doubles it to 12 parts, and we can see how much blue and white are needed to make 12 total gallons of mixture. Andrea draws the same initial picture and notices that if each rectangle represents 2 parts, that's 12 total parts. Alex's method is much more concrete. Andrea is using her tape diagram as a recording tool, which is a nice transition to being more abstract and more efficient. If we increase the size of the mixture from 12 to 72 gallons, let's examine what each might do. How many times would Alex have to proportionally increase this picture to get to 72 total parts? He might persevere, he might count wrong, he might give up, and he might wonder if there's a better way. Andrea uses her reasoning from before to determine that each part must represent 12 gallons and finds the number of parts for blue and white much more efficiently. Let's switch to setting up a proportion for the same problem. First, we focus on the fact that we are looking at gallons of blue paint, white paint, and total gallons. So words might help us keep track of things. We'll focus on one color here compared to the total. The value of the ratio of blue to total is 2 to 6, and we need a total of 72 gallons, where the amount of blue is unknown. Let's remember that B does not stand for blue, but rather the number of gallons of blue. Then we solve the equation to determine gallons of blue. We remember that blue and white together make the total amount, substitute in what we know, and arrive at the amount of white. In this session, paint mixture cards provided a visual and a context to explore proportional reasoning, using tape diagrams and equations to solve problems, and analyzing some common student misconceptions along the way. We hope you enjoyed it.
Thanks, Mark. That was great. The Center for Mathematics and Teaching is the home for all MathLINks programs. These include Common Core programs for grades 6 through 8, customized intervention programs, and professional development. You can learn more about these programs by visiting our website at www.mathandteaching.org or by contacting us directly. Thanks for joining us. See you next time.